Swayam Prabha. Digital India. Educated India.
Yeah, so what I wanted to talk about today is actually a unified way of looking at all these problems. So this is at least I find it very elegant. So really, you know, all the algorithms that we have seen can be seen as an instance of solving the hidden subgroup problem. So let's define that. Let's try to unify you know, the ideas that we had so far, and let's see now. So now, you know, we finally broke factoring and discrete log in the course. So now we're looking to figure out ways to recover, right? So we want to recover from this. So we would like to find problems in cryptography, or problems on which cryptography can be based, that are not vulnerable to these types of attacks. Okay, so the spoiler is that basically we will see that, you know, this period finding, Simons, Bernstein-Vazirani, these different algorithms that we have seen can be viewed as an instance of the hidden subgroup problem over commutative groups. Okay, and we will see that for commutative groups we know how to solve this problem. For non-commutative groups, actually we do not know how to solve this problem, and in fact it turns out that our leading candidate for post-quantum cryptography comes from a non-commutative version of this hidden subgroup problem. So the leading candidate is, you know, lattice based cryptography. So we will talk next about that, and we will show that you know, if the non-commutative version of this, not non-commutative version, but if this problem over non-commutative groups were also easy, then we could not have used lattices either. Okay, so let's look at that. Okay, so let's try to unify some of the algorithms that we have seen so far. Okay, so let's look at some of the algorithms. Okay, so just to refresh our memories. So what was this Bernstein-Vazirani problem, if you remember? Okay, so here, you know, we had a function which was going from 0 1 to the n to 0 1, such that f of x is x inner product s mod 2 for some secret s, right? And the goal was to find s. This was this problem. Then of course, you know, there is the famous Simons problem, which we spent a lot of time on. Okay, so here you have f that goes from 0 1 to the n to 0 1 to the n, and this was L periodic. Okay, so if you remember, f of x was equal to f of x plus L, otherwise distinct, and the goal was to find L. Okay, and then, you know, you had period finding. So here you had f, you know, Zn to Zn, and f of x is f of x plus L is equal to f of x plus 2L, and so on. Okay, and so the goal is again to find L, right. So we have talked about this a little bit in the context of a generalized Simons, right, that I want to think of the range as just a set of colors, so unstructured. Okay, so think of range as colors. And what is our quantum algorithm? So, by now you know we have revised this many times, right. So, you prepare a superposition of all inputs, right. Then you apply your function, right. Then you measure the function register, so this gives you a single random color. Okay, then you apply QFT. You measure and get clues, okay, and then you use clues to find the solution. Okay. So, what we are going to see is that basically for this hidden subgroup problem, we will see that it captures, we will define it and we will see that it captures the algorithms that we are discussing. And what we will see is that in fact, you know, whether the group is commutative or non-commutative, you can do all these steps. Okay. But for non-commutative groups, we do not know how to do this step, the last one. Okay. So, we do not know, I mean, having done the first several steps, we will get some clues. In the case of commutative groups, in specific examples we have seen, right, for period finding, we have seen how to use these clues to get what we need. It will turn out that for other problems, we do not know how to use these clues to get a solution, to get anything useful out of it. Okay. So, current cryptography is relying on that. So, we will have to see how that pans out. Okay. So, let us define this hidden subgroup problem. Okay. So, let us start with an example. Okay. So, let us take, you know, Z24. So, this is 0 to 23 and you know the group operation is plus mod 24. And you know, let us consider H as a subgroup which is, you know, multiples of 4. Okay. So, I am just doing a sort of a quick revision of a little bit of group theory here. So, now what are cosets of H? Okay. So, these are basically translates of H, right. So, we have H and then 1 plus H is what you would expect. So, you add 1 to all the elements, right. 2 plus H, and so on, right. So, the problem that we will be given is that if we have some function that goes from this group to colors and this is, you know, H periodic. So, what does H periodic mean? that the color is the same for every coset of H. Okay, so for all values of all values in H, the color is the same, and similarly for any j plus H, for any shift of H, again all those elements have the same color. So it is H periodic, right? Yeah, and you want to find H. This is the problem. Okay. So as I already said, the question that we are asking is this problem, the HSP, solvable efficiently using a quantum computer or using a quantum algorithm. Okay. And as I already told you, the answer is yes if the group is commutative. And do not know otherwise. Okay, so commutative groups, right? So HSP over commutative groups will capture Simons, okay, Bernstein, Vazirani, Shores, okay, and non-commutative this is actually going to capture lattice problems. Okay, so something like shortest vector problem. We will define this later. Okay, and also graph isomorphism. So all this is really interesting. I mean, these reductions are really interesting. Unfortunately, in the present course, I do not think we have time to go into them very much. So we'll just say this. Okay, so yeah, so for non-commutative groups, you have these examples. These are applications. So, you know, shortest vector problem or graph isomorphism problem. This is an instance of the hidden subgroup problem over a non-commutative group. So, we will see a little bit what these non-commutative groups are. So, graph isomorphism, you know, it's hidden subgroup problem over the symmetric group. If you know what that is, we'll see what it is. And a subgroup of the symmetric group, which is the dihedral group, HSP over that will correspond to these lattice problems.